Okay, welcome back to STEM Online Academy. My name is Jason Masterakos, and for those of you who don't know, this channel is about advanced mathematics and physics, teaching you how to solve problems at the contest level, and also these contest level problems will be highly relevant to hard exam questions if you're in university. All right, so let's get right to it. Today, we're going to finally start ordinary differential equations, okay? And I'm going to pull up something here. I think it's very important that we do that. Let's go directly to, just give me a moment here. Okay, we're going to go to my simulation. This specific ODE that we're going to be looking at, y double prime plus y equals sine x. Okay, and I'm bringing up the model here. Now, most students solve this, okay, exactly the same way. And for most equations, that works, okay? But here, the method suddenly fails. And if that's ever happened to you, you didn't mess up. The equation is doing something deeper. And that goes into something else I want to discuss here. Um, I was a student once before being an actual mathematician slash tutor. I was a student before, and I took ordinary differential equations. Right? Most people think ordinary differential equations is just you use a method algorithmically, you plug it in, and it solves your problem, and it should be very easy. Turns out that's not the case. Okay, most textbooks teach you that way, but if you've actually taken an actual ODE class, you will realize it's much harder than you actually think. Okay, at a conceptual level. Okay, and if you go in there thinking it's just I use an algorithmic method and that's it, some sort of formula, you are greatly mistaken. Okay. Uh, when I was in university and I took this course, I had a professor who was very difficult, but I benefited a lot because he taught me a certain way of thinking that makes the techniques useful. Okay. And that's what I want to show you here today. Okay. So differential equations is much harder than you think it is. Okay. And we are going to discuss that. Right. I want you to look at this model. And I bring up the model because I want to show you the behavior of what's happening with this equation. Okay. Today you'll see why this is important. Okay. So we're going to be looking at this ordinary differential equation. So let's zoom in here. All right. So we're dealing with y double prime plus y equals sine x. This is the second order linear differential equation, constant coefficients, very standard. Okay, we're going to solve this homogeneous equation, okay, by doing the following. So let me show you the solution, or at least I'll highlight the important parts. Okay, so solution. It's right here. Okay, we're going to look at solving this guy. So what I'm going to do is, since it's second order linear differential equation, sorry, we're going to set this to y double prime plus y equals 0. Okay, this is a characteristic homogeneous equation. Okay, we treat it as a homogeneous equation, right? First, right? The homogeneous equation means you set it to 0. And then we get the characteristic, right? Go to the characteristic part now. Now we want to go to the characteristic equation. Okay. Q-U-N for equation. And you'll notice we get r squared, right? R squared plus 1 equals 0. So just a quadratic. We want to solve for r. Okay. So rearrange. R squared equals -1. Take the square root of both sides. I say for r plus or minus the square root of -1 gives me r equals plus or minus I. It's a complex number. Okay. So the homogeneous, right? So the homogeneous solution is, look at the homogeneous solution. What do you think it is? We have to put it like this, right? Y sub h, y being the solution, h being the subscript homogeneous, is equal to C1 cosine x plus C2 sine x. Okay, that's what we have here. So we got the homogeneous part down. Let's highlight here. That's the homogeneous part. Okay. Right. But notice that our second order linear differential equation is not purely a homogeneous part. It's a non-homogeneous part. It's non-homogeneous because the right-hand side is equal to function. It's not equal to 0. But since it's non-homogeneous, we have to find the homogeneous part, which we did, the homogeneous solution. Okay, this guy right here. Okay. And then we have to find a particular solution as well. So far, nothing surprising. This should be pretty straightforward. Okay. Now we need to look for the particular solution for this equation here. Okay. We want to get the particular solution. All right. Now, the right side you'll notice is sine x. Okay. All right. That's what we see. I've highlighted under here. All right. With red. The standard method of undeterminate coefficients states that, okay, so let's do the particular solution. So let's do the particular. Just one sec. So we're going to do the particular solution. So the particular solution. Going green. The particular solution. Okay. We have to make a guess for the particular solution. That's what happens. So our guess, here's our guess. Okay. My guess is going to be y particular. Okay, so 1 second. So y particular equals a sine x plus b cosine x. Normally, this would be the case. And the reason why I made that guess is because normally when we have a non-homogeneous differential equation, if the right-hand side has like trigonometric functions, we usually assume the y particular should be this. Okay. This is the correct guess in most situations. That's what I'm saying. Okay. In most situations, if you have a trigonometric function on the right-hand side of your non-homogeneous equation, this would be the case. But as I said, this is the correct guess in most situations. You'll notice that we're going to have a bit of a problem, right? What I mean by that is if we can prove that this doesn't work, okay? Let me go to the next page here. Okay, the next page. Just 1 second. Okay, so we know that our y particular, right? Y particular was equal to a sine x plus b cosine x. Okay, that's what it was. I'm going to prove that this doesn't work. This particular situation doesn't work. And the way to do that is to find y particular, which we have, and y a double prime particular, right? We want to substitute it back into our original non-homogeneous differential equation and see if it spits out right-hand side. Okay, so if we do that, let's get y p particular first, y p prime particular. That'll give me a cosine x, yeah, a cosine x minus b sine x. Right? If you can look here, b sine x, I found the first derivative. Now, if I get yp double prime, the second derivative, you'll notice I get negative a sine x, negative a sine x, okay, negative a sine x minus b cosine x. Okay, I get that. Substitute into our equation, so we're going to substitute. Substitute into the equation below. Okay, the equation below, which we stated, right, the one that we're talking about, which was the y double prime plus y equaled sine x. I substitute my information in here, so y double prime is negative a sine x, negative a, second here. Pen is acting weird. Well, hang in there, guys. The good part is coming, minus a sine x minus b cosine x. Okay, that's for y double prime. And then for y, we found was a cosine x, right? A cosine x. What's that? Y. Was it? Sorry. Y particular. A sine x plus b cosine x. Okay. But you'll notice that if we take everything here, this is supposed to equal to sine x. That's what we're supposed to show. You'll notice that everything cancels, right? Because if you have a like terms and simplify, a sine x minus a sine x, cancel, plus group the like terms and simplify, b cosine. My writing today. Time to get a new pen. B cosine x minus b cosine x. B cosine x. Cancel. You'll notice that this does not equal to sine x, right? 0 cannot equal to sine x. So that means that our guess was wrong. 0 cannot equal to sine x. I think you'll agree with my logic here. Okay, because everything is canceled. And this is where students panic, okay? So no need to panic. Let's have an emotional reset, okay? If you've ever reached this point and thought, I don't understand ODEs, nothing went wrong. The cancellation is the clue. That's the way what I want you to think of. Let the zeros, right? So let this 0 just sink in. Yes, it looks daunting and scary, but it's nothing to worry about. Trust me. Well, it's something to worry if you don't get the correct guess, but this alone tells you, already rules out something deductively, that your y particular was incorrect. You have to find a new one. Okay. All right. We want to talk about specifically what resonance means. And what I showed you earlier, right, in that mathematical model, you can go back to it just to show you. Okay. Right, let's just go back if it's working. Oh, no. It's not working right now. Let's go back to the whiteboard. Okay. I want you guys to understand what resonance actually means. Okay. So you'll notice that we had the homogeneous part of our equation, homogeneous solution. Okay. Right, that's the homogeneous solution. The right-hand side of our non-homogeneous second-order differential equation, this guy here, right? If it's equal to some sort of function of x, we call this the forcing term. Okay, so let me just point that out here, right? So the homogeneous solution that we had, okay, so homogeneous solution, that we had, right, was the C1 cos x plus C2 sine x, and this was equal to y sub h. That's the homogeneous solution. Now the forcing term, doesn't matter what I call it. I may call it capital F for force. Okay, so capital, yes, use capital F as a function of x, because it is a function of x, is equal to sine x. That's our forcing term, okay? Now the forcing term is already inside the homogeneous solution, right? That's what resonance is. So I want you to also see this also as an application, right? Okay, I'm using some physical terms here, right? Forcing term, resonance, right? That's the system's natural frequency, okay? And what I showed you earlier, I wanted to bring it up again, but my simulation is not working right now, is to show you that the system has natural frequency and that it matches the forcing frequency, right? That wave, those waves that I showed you earlier at the beginning of the YouTube video, I just wanted to show you that was actually a phenomenon called resonance, okay? So in other words, you're trying to add something, right? Trying to add something that already belongs to the solution space, so your guess collapses. You understand? You can't add something that already belongs to the solution space. It doesn't make any sense, okay? Now here's the structural fix to all this, right? We want a structural fix to get a correct y particular, okay? Our y particular here, all right? So we want to get a correct y particular. When overlap happens, we're going to multiply by x. Okay, that's right. Let's go to a fresh new page. That's why no one's getting confused with the old stuff. So we're going to go over here. So new guess. Let's do a new guess. New. New guess. And my new guess, right, is the following. Y sub p, y particular is equal to x, parentheses, a sine x plus b cosine plus b cosine x. Okay. This, right, this forces the function out of the original solution space, okay? And it creates independence, okay? So anytime when you have some sort of overlap that we had with our initial y particular, you have to, that mainly tells you that you have to look for a new function. And quite often that new function, that new y particular should be a multiple of x. But in this case, yes, keep the a sine x plus b cos x, but just multiply by a factor of x. And this will help, right? This is going to be the solution. Okay. Now, if we differentiate, right? Right, briefly, right? If we differentiate, after substitution and solving coefficients, you should get this. You should get yp, y particular, right, is equal to negative x all over 2 times cosine x. Okay, I'm not going to go through it. You can verify that. I want you guys to verify. It's just algebra and some basic calculus, right? Right. So just by differentiating, right, and then doing the same substitution again with our new y particular, right? This guy here substituting, you should get your y particular to be negative x over 2 cos x. Okay. And let me explain why this will work. If you multiply by x, right? If you multiply by x, this increases its linear independence, okay? So if you guys, I'm just assuming you guys have a background in linear algebra, right? It helps you watch my videos, okay? If you're pre-registered in linear algebra, that would be great. Multiplying by x actually increases linear independence, so you should know what linear independence is, okay? You are actually stepping outside the original solution space, and the resonance isn't a trick. It's just, as I just mentioned, linear algebra. Again, linear algebra. And the forcing function lives in the same vector space, okay, as the homogeneous solution. So we extend the basis. In other words, your y particular, you want to be able to extend its basis, okay, by multiplying by a factor of x, which will increase its linear independence. Okay. Now, let's talk about its physical interpretation. Okay, let's talk about some physical interpretation here. The physical interpretation. Okay. Now, this is very important. In physics, right? Um, this equation models something called a forced oscillator. Okay, so if you think physics, you probably know that this represents a forced type of oscillator or oscillating mechanism. When forcing frequency matches natural frequency, amplitude will grow. Okay, and this is why we come to this y particular simplified as negative x over 2 times cosine x. Okay, notice the factor of x. Right? Notice this factor of x here. Kind of have it. Amplitude grows linearly. This isn't a coincidence. It's just resonance in a particular motion. Okay, that's all it is. All right, that I want you to understand. Resonance doesn't mean you made a mistake. It means the equation is revealing structure, and the method didn't actually fail in the first place. It just exposed mathematically something much deeper. Okay, look at this. If you enjoy all this, right? Right. Hope you've enjoyed my approach to solving this. This is fun. ODEs are fun. All right. All right. So as I said, if ODEs have ever felt mechanical or confusing, okay, it's usually because the structure wasn't explained either by your professor or whatever else. Once you see the structure, that fear will disappear. Okay. If you want to train this way of thinking, where methods connect and align with structure, okay, I've written a book called Advanced Integration Techniques for strong undergraduates, not only strong, but intermediate to strong undergraduate students. You should be intermediate to strong, you're in university, okay? Uh, you can find it in the link below. And I also offer one-on-one coaching in calculus, ODEs, or differential equations like this lesson today, and also in another subject, physics, okay? All the links will be below at the end of this YouTube video. And remember, struggle in math isn't a verdict. It's a signal that you're actually closer to understanding. Okay. I hope you guys enjoyed this video. I'll see you again next week. Remember, it's Tuesdays, Wednesdays, and or Thursdays. I make my YouTube videos, pre-recorded YouTube videos. Stay tuned. Much more interesting stuff is coming. We're getting into some cool stuff, a big variety of stuff. Have a great day, guys. And don't forget to like and subscribe. Please like and subscribe. That always helps the YouTube algorithm and me as well. Bye bye, guys.